What's up, y'all? I'm yet to find a video that explains Green's theorem like actually well, so here I go. Let's say we have a parametric curve that just literally goes in a circle, like that. Let's say it goes in this direction, counterclockwise. Say we also have a vector field, mn. This is the x component, this is the y component. And let's say that n is actually equal to 0, so there's no y component. So I ask you, let's find the line integral of our curve. This is our curve. So we find the line integral of our curve along in the vector field. So in our case, the vector field only has a y component, so it's just m dx. So Green's theorem states that it's the double integral of in the region of partial n partial x minus partial m partial y dA. Now I ask you, why is that? Well, if we look at our parametric curve again, let's say I want to find how much work was done just literally in between. So like let's say like if it was a conservative vector field, if we have a particle that goes from there to like right on top of it, just up there, well, normally if let's say like it's like that, the vector up there is like that, and the top vector is like that, then well, it's gonna have work done on it here, but it's gonna get canceled out on the top, right? So the net work done will be 0. So we want to find, so from the top to the bottom, we want to find how much work has been done. So usually on a conservative vector field, in a closed curve, this is usually always 0. Like if you just go all the way in the curve. But let's say like if the bottom vector is something like that, but the top vector is something different. Let's say it's like that instead. Well, now there's like a net rotation, right? So you're gonna have to like, so how do we find how much work, total work was done? Well, if you think back to integral calculus, like if we want to find how much the vector changed from here to here, well, we can just integrate from the bottom to the top of partial m. So we have a bunch of vectors going like this, right? So that's m. So we want to find how m changed with respect to y. So like partial m partial y. So we want to find partial m partial y dy to find how much our vector changed from the bottom to the top. And we want to find this value. So this tells us how much it changed. So like it goes like, there's a different vector in the top and bottom. So we have net work being done. So we want to find that value, like the net work between 2 points, all the way around. So we want to like do that on every single point. So yeah, all along the curve. So that ends up becoming dA. So if we think back to the curl, let's say we have 4 vectors that go like this, and like that, and like that. And our origin is right here. And we have is going in a circle. Well, here we have no rotation. And how is curl defined? If a curl is positive, if we go from the bottom to the top, so partial m partial y will be negative, but we want it to be positive because we want counterclockwise rotation to be defined as positive. So it's negative partial m partial y. And like along here, n became more positive, so partial n partial x is positive. So our net rotation was positive. So all in all, basically, we're finding how much net rotation there was between 2 points, and we do that all along the curve. That's pretty much it. So to sum it up, we have the double integral in the region will be so like, okay, also like what I meant to touch on was that we showed this in the m direction, But we can do the same thing literally in the n direction as well. And that shows us in nx, in n partial x. So the whole integral, to find all the work that's being done, we can just find the double integral in the region of partial n partial x minus partial n partial y. And that will just all be on dA.